Good evening, ladies and gentlemen. My name's Andrew Ogden. I'm the current chair of the South Eastern branch of CIWEM, and I'd like to welcome you here this evening to what I hope is going to be a very informative talk by our guest speakers, who I'll introduce in just a moment. First of all, I'd like to thank you all for coming, because obviously we wouldn't be able to arrange these without your attendance. The subject of tonight is perhaps very inaccurately put as fracking an industry perspective. What it perhaps really should say is shale gas exploration and exploitation, an industry perspective, but that would be rather long to fit on our programme card. So the term fracking is very loosely explained, very loosely used, and will be explained further by our guests here. Now, the proceeding will be that we will go through two presentations from our guest speakers, and then we're going to hold a question and answer session, because we're sure that perhaps there are far more questions to be asked than can be answered in merely the slides. And to orchestrate that and to chair that session, we have actually the current president of CIWEM, Mike Musgill, sitting up the front here, who's going to be leading on that. So, on to our guest speakers. We have three leading lights from Cuadrilla. Now, if you haven't heard of Cuadrilla, A, I don't know what you're doing here, and B, you must be out of the country for the past 12 months. I'm sure that you at least have an inkling that they are the UK's leading shale gas exploration company, and certainly have featured in the news, must be at least weekly for the past 12 months. Not too sure whether it's even more frequent than that. On my immediate left, we have Eric Vaughan. Eric is the World Services Director. I'm sure Eric will explain where that fits into the hierarchy. Next to Eric, we've got Nick Mace, who's their environmental engineer, and will be focusing on the environmental aspects. And then we have Mark Linder, who comes from the commercial services arm of the company. The presentations will be given first by Eric, and then by Nick, and then we'll go into the question time. And I think all three gentlemen are prepared to take your questions and possibly take any flack. We'll see how we go. I think that's covered pretty much all of it. All I will add is that for those who are members of CIWEM and for those who are not, you will know that we have recently issued a new policy position statement, which is available through the website. This in itself is 11 pages long, and there is also an independent review, which is a 48-page document, which is again available from the CIWEM website. At the end of the meeting, if my good colleagues from JOLSOC or ICE want to advertise their publications, if they have them, they're most welcome to. So, as they say, without any more ado, I'll hand over to Eric to lead off on the presentations. Thank you, Eric.
Thank you. So my presentation, basically I'll go over sort of the general shale gas exploration that we're doing, it'll be a little more general presentation, and then Nick will follow up with some more detail on, especially on the water flow back water, and we'll try and not spend not too much time looking at a PowerPoint and allow more time for questions, because I think most people like the question and answer session better than listen to me drone on. So the quick bit on Cuadrilla. Cuadrilla, of course, was formed back in 2007 specifically to look for shale gas in UK and Europe. That was sort of coming on the very early part of anyone that was looking for shale gas in Europe. It was more established in the US. And we basically looked at acreage here in the UK, so we've got a couple licenses here. We've also got stuff in the Netherlands and in Poland. Just briefly, talk a little bit about what is unconventional gas or shale gas. why we are primarily focused on the Boland Basin, a little bit on operations like drilling and fracturing, some of the environmental concerns and questions, and then a little bit on the economics there. So what is shale gas or unconventional gas? So it's a methane molecule from a conventional gas well, if it came in from the North Sea or one of the onshore fields. The methane molecule from a shale gas well, it's the same thing. Shale gas is just natural gas. Okay, it just came from a shale formation instead of a sandstone or a carbonate or basically the reason people call it unconventional, or how it got its title unconventional, isn't the gas itself, and it's not the way we drill or fracture or anything. That is not what makes it unconventional. What makes it unconventional is the source, the rock itself. So the geologist will know, this is just a, so this is just a picture of a traditional trap that you would normally capture oil and gas in. There'd be some type of sealing rock. The oil and gas would migrate from the source rock, which is usually like something like a shale, and over geologic time it would get stuck up there, and a traditional well would drill into that, into a more permeable and more porous formation, whereas shale gas, we're basically going after the target rock where the oil and gas was actually formed. Just a quick picture of just some shale and methane molecule kind of to scale inside the matrix of the shale. Shale is extremely tight. Pavement stones outside are more permeable than shale, which is one of the reasons that traditionally they didn't produce gas or oil from shale. So it took us a long time to figure out how to create permeability in the shale so that we could get the oil and gas out. Why do we target the Boland Basin? If you look at the BGS study, this is from the BGS study of the shale gas resources in the UK, and our license is this section up here. So that's our Boland Basin. That's where we've drilled the wells so far. It's basically Blackpool and Preston there, and all these black boxes are the existing oil and gas license that are already established onshore in the UK. A lot of those are for either coal mine methane or coal bed methane, but there's some traditional oil fields and gas fields in there too. This is just our license area. We picked it because it has the correct geology, so we knew that the shale was there. There was a lot of old 2D seismic that was run there. The age of the shale is correct. The depths that we thought before we drilled from the data that we could glean, the public data, the depths are about right. There were 4 wells that had already been drilled within this area. 2 of them had penetrated the shale, so we could see the shale was there. We could see the gas contents and actually see some of the cores. And of course, there's a history of oil and gas production in that area. To the southern end, just off down here, you can actually see one of the Formby wells there. There's an oil field in the southern part there. And then, of course, there's the oil and gas coming offshore. One of the other key reasons is there are pipelines that run right through the middle of that license. Those are the part of the national gas grid, loop around the country. So if there is gas there, if we can produce gas from these wells, it's not too far to any of the pipelines to get it into the grid. There's just some of the old 2D surveys. And the blue lines on all that, those are all the 2D surveys that were done in the area, mostly in the 70s and 80s, I think. Quick little bit on operations. So what we've done so far is drilled 3 wells, most around 10,000 feet, a little over 10,000 feet, to test mostly the Boland shales. We've only had 1 well that penetrated the Boland and went into the hotter mudstone, which is a shale underneath the Boland. We've also acquired about 100 square kilometers of 3D seismic acquisition, which gives us a lot better picture of the rocks. Some of the old 2D stuff, even with reprocessing, it's still not the best quality. And then the 1 well that was drilled back in the 80s, the Ellswick well, is still producing a little bit of gas, and and we've acquired that in the middle of our license there too. And then, of course, we have the well down here, which is different. It's not a shale gas well. It's a conventional oil well in a limestone. So here's some pictures of the shale. So this is what shale looks like for the, I say, the non-geologist here. One of the things that we look for in a shale gas well, we're trying to produce gas, are some of the natural fractures. I mean, the problem with shale is it's too dense, it doesn't have any permeability, and really the only way to produce the gas or oil from it is to have a fracture network through it. So we can only generate so much of a fracture with hydraulic fracturing. There has to be some type of natural fracture network in there too. So the white bits in there, all this is some of the natural fracturing and where basically calcite has formed in the natural fractures over the time. One of the other things that we really look for is for those fractures to be going in different directions. So, and you can see when we take cores, when we drill these holes, the wells that we've drilled so far are basically vertical holes, and the purpose is really to get the rock back to surface and look at it and measure how much gas is in it, how much organic content is in it, all that stuff. And but if you take the cores of this rock, if you just, to most people, if you look at the rock, you would never imagine anything that comes out of it. But if you take it, stick it in a tank of water at temperature, the formation temperature, and you see streams of bubbles will start coming out. This one actually isn't even a very good sample. So as I mentioned a little bit ago, we have been in the news. You see things about Quadrilla, and you see things about other companies now. So a lot of things on hydraulic fracturing, and usually see pictures like this, and we say, here's fracturing, fracturing's coming to town, and all this. None of these pictures have anything to do with fracturing. Okay, those are all drill rigs. So whether a well is being fractured or not is independent of the drilling. So this could be a well drilling a geothermal well, it could be a conventional oil and gas well, it could be a deep water well. I mean, the rig itself is actually used for water wells in some areas of the world. So you see that, and you see the article, and it has that. Fracturing has become this catch-all term for basically anything to do with oil and gas now. And so it's interesting to someone that's been doing fracturing for over 30 years, and then you see something like that, it's like, well, that's not fracturing. And I actually talked to a guy that was a driller, has been a driller for 30 years, and he came up to me one day and said, I didn't even know that for the last 30 years I thought I drilled wells, but apparently I've been fracturing them. And the fracturing in the UK has been going on for quite a while, actually. Now the fracs changed. There's lots of different types of fracs. It's not all, you wouldn't use the same frac in a shale gas well as you would in say a small carbonate or a sandstone, a tight sandstone well or something like that. So the picture in this frac was back in 1992. This is when I first came over and started doing fracs here in the UK. Now this frac was very similar to the fracs we do now. It was a big, it was a slick water type frac, so lots of water, not a whole lot of sand, fairly high rates. It was more than one stage, but it was on a vertical well. And this was just outside of Chester. It was actually fracking in coal seams. This is frac equipment sitting on the pre-salt well. So this is the frac that we did on our shale, the one shale well here that we have fractured. Mostly on a high volume type shale frac, mostly you have water. So these are all tanks of water. They look like shipping containers, but they're actually water tanks. These little bits down here, those are pumps. The fracturing process itself, especially on high volume water style fracs that you do on these shales, is really just a big water moving exercise. We're trying to get water on, we're pushing water down the well, and then out through some small holes in the pipe at enough pressure that it cracks the rocks, and especially on where there's natural fractures in there, it'll start to follow those. And we're filling those cracks with sand, just silica sand. It's actually mined here in the UK, so that when we relieve the pump pressure, we stop the pumps, then when those fractures try and close back up, they can't close all the way, the sand's in the way, squishes a little bit of the water back out, and then gas or oil can flow back to the wellbore. Goes on lots of other places. We do it in the North Sea all the time. And so anybody that wants to say, I'm going to use frac-free gas, can't use any gas in the UK, because someplace that gas has been hydraulically fractured. So Lots of boats. Boats are expensive though. So. They do it in Poland. Everybody's heard of Halliburton. This is Halliburton fracturing in Poland. And then here's a picture of North America. So one of the things that comes up all the time is you can do this in North America because you're in the wide open spaces, there's nobody around. So this is a frac just outside of Fort Worth, Texas, which is actually the home of modern shale gas development. So the county in Texas where they had started the shale gas, the modern shale gas is in Tarrant County, Texas, which actually has a higher population density than Lancashire. So sometimes it is done out in the middle of nowhere in the U.S., but not always. When we do the fractures, a lot of people want to know where they go, how long are they, how tall do they get, and how do you know? Like, how do we know that the fractures aren't growing thousands of feet vertically and going up someplace where they can contact the water table? So one of the ways to do that is we can monitor them. It's basically called microseismic monitoring. We can monitor the microseismic activity when these rocks crack. It makes enough noise that you can pick that up through either downhole arrays or from near surface arrays. What this picture is two well bores. So this is looking at it from above, so it's a horizontal well. And that's the green is the one that they're actually fracking. And then the red one over here is an offset well, and it probably has the microseismic array inside it. And when you frack, if the vertical section of the well was down here in the bottom right corner, you'd be pumping down and pumping out the well, and you would start out here near the toe or the end of the well, and you would do a frack down here. So all these little green dots are seismic events that they could hear when they did the first frack. So they would have fracked in there, picked up that, they would have set a plug in the pipe and sealed it off, and then done another frack. So the kind of dark purple would have been the next one they did. And you can see, so when they did the second frack, there aren't any purple events in the green, and there aren't any farther back up towards the heel. So you have to divide the well in these sections. So this well would have had 1, 2, 3, 4, 5, 6, 7 or 8 stages there, it looks like. And they would have sealed off the well in between each one, done each one individually. The reason that you have to do that, and that's also one of the reasons that it makes it very difficult to come back in later and refrac one of these wells. If you want to come back and frac it again later, it's hard to do because at that point, all the part of the whole well is open at that time, and you can't isolate all those little individual sections, and you can't get enough energy to down the well. You can't pump the water in fast enough, basically, to do the whole thing at once. All the water would go whichever group of that area was the easiest for the water to go. Most of it would just all go there, and it wouldn't fracture, it wouldn't stimulate the whole well. But from this information, this is a view from above, so this is showing you the frac lengths, how far out they go from the well bore, and then from that information, you can also look at it from the side. So this was a study that was done. This particular shot is from back in 2010, but they've updated it several times since then. And what it's showing is the jaggy bit down at the bottom of the graph is the highest or the shallowest point that they got a seismic event from when they're mapping the fracture, and the bottom is the lowest. So it's basically showing how tall the frac could possibly have gone and how deep. And then all the blue lines up at the very top are the deepest aquifer within the whole county that well was fracked in. So there's several thousand fractures. Each one of those would have been a frac. The red line up the middle is the average depth. It's hard to see on this, but that's 8,000 feet. So it's 2, 4, 6, 8, 10 on the vertical scale there. So one of the other things that you can kind of see on this graph is the shallower the wells get when they fracture, the less frac height they have. And eventually you'll get to the point, like probably 1,500, 2,000 feet depth, that the fracs won't grow vertically anymore because the rock stresses change and it's easier for it to grow horizontally. So once you get to a certain shallow depth, the stress on the rock is such that if we inject in, instead of making a vertical crack in the rock, it's easier just to separate the layers and it'll just open that way. So you have a horizontal fracture at that point, which is one of the reasons it makes it very difficult for fracks to travel up to really shallow depths where say, an aquifer is or something like that. One of the other reasons we know how the fracks react and what's actually going on downhole, because you can't physically go down there and measure it all the time, but sometimes they have. And these are some pictures from some work done by Warpinski where they did mine back experiments. So they drilled wells, they hydraulically fractured them, and then they mined into it and mapped out where the fracks went, what they looked like, and that it's some pretty interesting stuff on that. Of course, we see a lot of stuff on water, good group for the water, and we hear lots of things. Oh, water, fracturing is going to contaminate the aquifer, and taps are all going to set on fire, and that I mean, one thing, if you're on mains water, I can promise you your tap would never set on fire from hydraulic fracturing. Okay. There are some places in the U.S. that you can do that. You can light your tap whether there's hydraulic fracturing going on or not, but those are all people that have pretty much individual water wells that are coming straight into their house. A lot of places, especially in Pennsylvania, some areas in Colorado, lots of areas where there's coal, there's already methane in the water, and normally when you put a water well in, you put a methane vent on it and to keep it out of your house. But in reality, the depths that we work at in shale, the fractures that we create in shale, there's just no way they're going to come back up into a shallow aquifer. From the measurements that we've seen, from the mine backs, from that, we hope that a frac will extend a couple 300 meters away from a well bore, because the farther that goes, the farther apart we can put our wells. At least, which means the fewer number of wells we have to drill, and which of course is cheaper. And unfortunately, we can't get the fracs to go far enough that we can put the wells really far apart. If you can get a couple 100 meters each direction away from a well, you're actually doing pretty good. And we also monitor all around our wells. So we put water monitoring wells in just to show that we're not putting anything in there. It is possible to build a well so that you construct a well so that you can get gas from mostly from shallow gas formations, not necessarily from the shale, but there are places, especially in Pennsylvania, that they have contamination or they have methane from shallow gas-bearing zones that'll leak up the side of the wellbore, and then if it's connected to where an aquifer is, it can leak up that way. But you're not getting frac fluid or anything. Again, it doesn't really have anything to do with the fracturing part. It's all above that. It's all up in the actual well construction. The blurb on this, I don't think there's still not been any place that's confirmed any frac fluid in an aquifer. Okay, I think there's one case back that the EPA did, I think it was back in the 80s or something, where they fracked one well and there was an old well that nobody knew about. It had been abandoned, had been drilled like in the early 1900s, and they basically fracked one well and it came up the other. But they still, even on that one, I don't think they could find any frac fluid. I think they found some drilling fluid in an aquifer on that. But certainly on a modern well, there's no cases that have actual frac fluid gone anywhere up in an aquifer. And as I said before, you can't construct a well poorly and let gas travel up and down the borehole and have natural gas go into an aquifer, but you can't really get the frac fluid. And the UK onshore, there's a little over 2,000 wells have been drilled, and the industry here, I think since 2000 they were averaging about 30 wells a year, between 30, a little over 30 wells a year drilled onshore. The water that we use for fracturing, what we've used so far, is just mains water. And one of the reasons for using mains water is it reduces the truck traffic. If you're on a site, you can get a mains line going into it. You don't have to truck any water in. It reduces truck traffic, makes us happy because it costs less, makes everybody around happy because there's less truck traffic around the site. One of the other good things about mains water is it's already been treated for bacteria. One thing you don't want to do in an oil and gas well is put a bunch of bacteria down there, because they really like it and they can actually plug up your well. And so normally if we're using other water, then you would treat it with some type of biocide, just like they usually do with drinking water. You don't have to use drinking water. Again, it's basically because it's more convenient, and if it's available, we can use it. You can use water from streams, you can use ponds, you can use seawater. I've used the effluent from wastewater treatment plants. It doesn't have to be perfectly clean water, you just don't want to have any bacteria in it. And for the type of jobs that we're doing, the type of fracks that we're doing, it's called a slick water frack, which basically means we're putting some type of friction reducer in water. It's one of the, one of the styles of fracks, I would say, that use the least amount of chemicals. And so the only thing that we're really putting in there is a polyacrylamide, which is just a long chain polymer. It's non-hazardous. And what that does is reduce the friction of the water as we pump it in down the pipe, so that it doesn't take as much pressure at surface and it doesn't require as much pumping equipment at surface to push the water in. You can buy the same stuff at the agriculture store or at the let's say the greenhouse or the flower I don't know the right word, the home center, yeah. And but what we normally call there is swell gel. You ever see a little jar of swell gel? It's the stuff you put in your flowers so that it absorbs water and it holds the water. That's polyacrylamide. If you're a farmer and you're going to use it over a big area, it's called broadleaf P4, and you can buy it at the farm supply there too. And of course, the other thing we put in is sand. When it comes back out, it's been in contact with the rock, so it'll pick up some of the minerals from the rock, especially salts. Nick will go into a lot more detail on the water, and normally we're gonna, if we pump in, let's say 1,000 cubic meters, we should get back somewhere between 20 to 40 or 50%. I think it just depends on the shale and the area that you're in. Some places are as low as 10%, and some shales actually produce more water than what you put in. So, one of the main things you want to do, though, it's one thing that's happening in the U.S. a lot now, is to recycle the water. So that water that flows back, instead of having to send it off to dispose of it or treat it, is you want to treat it so you can just reuse it, which again reduces the freshwater requirements and also reduces the traffic going around the site. Of course, you had the report from here, looking at the scale of shale gas and what would happen if this industry actually takes off and develops, and looking at the water use on that. And although we sort of have this reputation that we're going to use lots and lots of water, in the big scheme of things and in industrial use, it's not really that much. And so it's less than 1/10 of 1%. Now, what you can have is in certain areas may have different water use restrictions than others. So in some areas there isn't very much, say like drinking quality water. So if you can use brackish water or produce water from a well that wouldn't meet human consumption standards, we can use that water. Or like I said, anything seawater, effluent from the treatment plants, that's fine too. One of the other things is you have to look at the other things that would use the water instead of shale. If shale gas or natural gas replaces coal, you actually use less water just to process the coal, not counting the actual power plant, but just mining the coal and cleaning the coal and sending it to the plant uses a lot more water than the same energy output you get from a gas well. And actually nuclear uses more water. And, a little bit on economics and also on why it's important to have natural gas, or in this particular case, natural gas from shale or shale gas. One of the things that's happening here right now is the North Sea is on a decline, pretty steep decline on natural gas and oil. And I think we're importing, it's like what, 50%? Is 50% the right number now? 50% of the natural gas right now is being imported. And that's expected to grow up to, I think 70, I've heard 70 to 80%, depends on what study you look at, between 2020 and 2030. And what that means is that orange blob is money that is basically going out of the country. So it's either imported from Norway, the LNG is coming mostly from Qatar and Algeria, and so that money is all going someplace else, and all those jobs are someplace else. I think they said some bit on TV last night, and you hear on the newspaper and on the news, we've got to keep the lights on, and we have these issues with the power demand. And one of the things that's also happening here is instead of getting cleaner and greener with the energy, it's actually going the other way. Okay, what's happening is we're burning more and more coal. Okay, so this is from 2011 to 2012, gained about 10% in coal burn. Okay, and they haven't actually, or I haven't seen the numbers yet from 2012 to 2013, but I know the gas hasn't replaced very much coal, if any, in that time frame. And then this is just for electricity. Okay, so natural gas is used for a lot more than just electricity. So most of the gas is not used for electricity. And roughly, depending on the year and the number, it's roughly a third for electricity, a third direct to homes for heat, and a third for industry. It's kind of a rule of thumb. You can see the exact numbers depending on the year. So what that actually means is if tomorrow we switched over to 100% renewable electricity, you're still importing gas. Okay, that you're still taking money and sending it someplace else. This is the national grid from today. So this was today. Really neat website, gridwatch.templar.co.uk. Can gives you a real-time look of the electric grid. And what you see on here is the red line. That's combined cycle gas turbines. So that's natural gas burnt to create electricity. The black line up the top is coal. Blue line at the bottom is wind, and the green fill-in is the nuclear. So you see the nuclear is nice and steady. Wind kind of goes up and down as the as the wind changes, and then a lot of the on and off of the grid and the peaks and the troughs in the grid is all made up with natural gas. The more peaks and troughs you have, the more natural gas you want to use. So the more wind that we stack in here, then the more you need natural gas to balance it out. If you look back on the windy days, burnt more coal and just dropped the natural gas. So every time the wind blows, we actually increase the carbon that we're going in the air because we're pulling back the cleaner fuel and keeping the dirty fuel going. So eventually we've got to break that habit and try and get the coal down and the gas and the wind up. Again, this is the same chart as before, and this is what certainly the shale gas industry, and this is why the government is trying to push the shale gas industry, is to try and fill some of that gap that is being spent on importing the natural gas. Quick blurb on the industry. We're not a subsidized industry, so you're not getting subsidies to drill shale gas wells. If the Boulton Basin developed, probably about 50 billion pounds would be spent on that development. There are various different scenarios for jobs. The Institute of Directors peaked out at about 74,000. I think the lowest one I've seen is about 20-something thousand jobs. But they're all a little bit different. You have to really look close and see what they're measuring the jobs against. And obviously, if we can get to that type of development on gas, it will make a significant benefit to the energy security. And then one of the other differences is if we produce the gas here, we're certainly under a lot more stringent controls. We want to have green completions, which means we don't vent methane, we don't have leaks of methane. Methane going straight to the atmosphere is a very potent greenhouse gas, so you want to minimize any emissions to that. And of course, as a gas company, we want to sell it. We don't want to vent it anyway. But if it's completed in other areas of the world and you're importing it in, they don't necessarily have those standards. And technically, the size of these pads and the size of the development is small compared to other types of generation, for like per BTU to generate power. The community benefits, these have been recently announced. The local authorities are getting all the business rates now, 100% of the business rates. During exploration, for every well that we frack, we're putting 100,000 pounds into the local community, and then if it ever makes it into development, there's about 1% of the revenues that go into that local community, and there's still debate on what constitutes the local community. Is it the local village? Is it the county? Is it sort of a little bit of both? And I think they'll be debating that until the money actually starts to come in on that. Quickly, Cuadrilla, we're still early in exploration. There's a lot of stuff that comes out that shale gas is going to be the savior of the planet, and others it's going to be the death of everything. And in reality, we don't know a lot about what kind of volumes are going to come out here. We're still in exploration. There may not be anything. Okay, so we don't know if this is going to be economic or not. That's why we're trying to do the exploration wells. And it probably needs to be 20, 40 wells are the numbers that I've heard kicked around on wells to explore, to try and get some kind of idea of what the economics on this and how much gas will we actually be able to get out of the ground. Will it be worthwhile? The industry is well aware of the risk. The wells are built. It's basically the same as every other oil and gas well. Similar standards, or the same standards actually, as what we build in the North Sea. And again, it's the same as the wells that have been drilled onshore for a long time. The benefits to the local community are a plus. And then one of the things that we're trying to do is talks like this and try and get more information out, and especially in the areas where we're working, like up in Lancashire, we're trying to get more information out to the local stakeholders. And I'll zip it over to you.
Yep. Okay, thank you, Eric. Right. Good evening, ladies and gentlemen. So, Nick Mace, environmental engineer for Cuadrilla, work in the HSE department. There's about 2 specialist environmental advisors working full-time in Cuadrilla. We do have support from Centrica as well, and we're plugged in with Arup, who are conducting our environmental impact assessment. So, relatively small team, but well supported within our supply chain and investors. I spend pretty much 50-50 time in terms of technical work, but also PR work and community engagement, so trying to promote the message of good environmental practices, our environmental management systems. So hopefully today I'll probably enlighten you a bit more about the management of flowback fluids. There seems to be a bit of mystique around this waste stream, so I'll focus on that today. But as we go into the Q&A sessions, I'm sure we'll probably touch on other environmental impacts. Okay, so as mentioned, just focusing on flowback fluids. So it is a waste stream. Just going to understand how the waste is generated, the regulations surrounding the management of flowback fluid, the waste management hierarchy and the application of that process, treatment options, and then we'll look at a few conclusions of how we're managing the flowback fluid. Okay, so in terms of generation, it's quite important to understand what activity we fall under. It might seem quite obvious in the oil and gas sector, but we also fall under the mineral extraction sector. Because I'll touch on this in the regulation section, but as a mineral extractor, that means we fall under the Mining Waste Directive. But if you ask people like Eric and other people in the oil and gas industry, we're not a mining company, we are oil and gas. But because of the technical language used in the directives for prospecting for natural gas and minerals, we do fall under that directive. In terms of what comes out, the flowback, the composition, it has been deemed non-hazardous waste stream by our internal analysis. That's against WM2, which is the EA technical guidance for waste classification. As I said, and what Eric's has touched on, is you're going to have elevated salts, minerals, but also very low levels of naturally occurring radioactive material. Now we need to put that into a bit of perspective. We've done a number of studies on this to try to get the message across not only to professionals but also to the layman in the local community. So at Priest Hall, when we did have flowback fluids, it peaked at 90 becquerels per litre. On average, it was about 27 becquerels per litre. If you look at a comparison, Brazil nuts, looking at the norm that's contained in that, it's the same radionuclide, which we find in a flowback fluid of radium-226. You get about, for 6.8 grams, about 1 becquerel per litre, and that's the legal threshold which you need to apply for an RSR permit, which is a radioactive substances permit. So really, you're looking about 600 grams of Brazil nuts grinded up, thrown into a litre of water. That's how much radiation is in our flowback fluid, so incredibly low levels. But nevertheless, we are regulated by the RSR permitting regime. So in terms of quantity and how much flows back, Eric touched on this, it depends how much you inject, but that can range in between 20 and 40%. I've got a few figures here from a couple of plays over in the US. In the Barnett, you got 308%, right down to the Marcellus, which is looking at about 12% flow back, so it does range quite significantly. Flowback fluid in itself is pretty much not a new phenomenon. Wastewater has been produced by the onshore oil and gas sector for a number of years now. We've got Wyche Farm in Dorset, one of the largest onshore oil and gas facilities. According to DEX figures, there's 93.8 million barrels of produced water, exactly the same properties, saline, minerals, it's got norm in it. Conventional wells tend to use this water to re-stimulate so they can re-inject, but the vast majority of that will either go for treatment plants, both onshore as well as onshore treatment plants receiving North Sea flowback fluid as well. We're working with a contractor at the moment for disposal facilities, and he's assured me that there's about 100 to 120 tonnes per month goes through his treatment facility. So again, it's not a new area which the industry needs to tackle. It's just more probably getting the perception over to the public. Okay, so regulations. I could probably draw about 20 slides on the regulations that apply to the oil and gas industry onshore. These are the key ones which we're working on at the moment, but there are other ones on there which you'll find on most construction sites and other developments. So environmental impact assessment, initially this wasn't a requirement for the industry, but Cuadrilla has taken the position, and this has now been firmed up by the European Union, that if you're going to carry out hydraulic fracturing operations, you will need to do an environmental impact assessment. We've employed Arup Consultancy to carry that out as a position of objectivity, not a position of advocacy. So they'll be doing a series of modelling and analysis of a number of chapters, so archaeological, radioactives in there, waste management, resources, air quality. They will then issue the EIA for submission to the local authority, and that goes through a 4-month consultation period, so quite an intense process. Within Cuadrilla itself, one of my principal positions is to apply to the Environment Agency for EPR regulations, permitting, so that's the mining waste, radioactive substances, and an IED. For the mining waste, this is really concerning, that whole discussion what we mentioned earlier about does it fall under the mineral sector? Yes, it does, so the mining waste applies, and this deals with all extractive waste streams. So you're looking at both drilling muds, cement, but also the flowback fluid. What we have to do in the mining waste is first of all develop a site condition report, so we have to do baseline surveys, and that collects data on air quality, groundwater, surface water, soils. We have to then present that to the EA, also do a desktop research into what the historical impacts have been on the site before we've even arrived there. That then provides us with the benchmark, so when we come to do P&A, which is plug and abandonment in Could be a couple of years' time, could be hopefully for us in about 50 years' time. We've got then the benchmark which to restore the site to its original condition. Within that, we also have to produce a waste management plan, environmental risk assessment, and these look at the amount of waste produced, destinations they're going to, and application of the waste management hierarchy. So quite an intense process. And that's pretty similar for the RSR permit, the radioactive substances. Probably the only key difference between those two is that we also have to have a letter of agreement in principle. So we have to demonstrate to the Environment Agency that we've got facilities to dispose of the flowback fluid that returns to the surface. The Industrial Emissions Directive, this is to do with flaring. We have to apply best available techniques to reduce the amount of methane being emitted. So you're looking at probably an 800-degree burn. That gives you a conversion rate of about 98% to CO2. There's other permits that we could potentially apply for, groundwater and surface water discharge, but this is done on a case-by-case basis. Just to probably flick over onto groundwater. Some of you may be familiar with the position statement from the Environment Agency and technical guidance called GP3. This kind of summarises what GP3 says for the industry. Is that if you're operating in source protection zone 1, this is where a lot of the groundwater abstractions licences are for supplying the mains and the local communities. That decision will be pretty resolute from the Environment Agency. We will not be allowed to drill and hydraulic fracture in that area. There are other source protection zones 2 and 3, and as you said, we need to apply BAT, and that's best available techniques. So you'd be looking at multiple casing, multiple cementing, obviously applications of the oil and gas onshore guidance. Again, we can go into that into great depths, but this is all regulated by the HSE. But something which we have to demonstrate now to the Environment Agency that we've got good well integrity. There are other regulations, abstraction licence, that's something that we used quite successfully at Balcombe. We drilled a groundwater monitoring well. It was artesian. We applied for a temporary licence for 28 days, and that supplied water for the drilling process because we use water-based muds. That reduced truck traffic off the road, provided a very useful source of supply, especially when we're having a few issues getting trucks onto the site. Also, back in, I think it was 2011, Royal Society did a report. They recommended that all sites going forward, all operations involving shale gas and hydraulic fracturing should conduct an environmental risk assessment. DEC are currently drafting up guidance on this for the industry. We're going through the process now with local communities, and this is a high-level process. We look at the risks, we take on board community engagement, we ask them what risk they perceive. We then have to reply to them with the necessary mitigation, present that back to the local community. Then when we've got our full high-level environmental risk assessment, we then submit that to DEC, not for approval but for assessment. And then we move forward into the full environmental impact assessment. Now, I'm not aware of any other industry that has to do that, an ERA. You can build a nuclear power station, but you don't need to go through an ERA process. So this is quite unique to the industry. Okay, so in terms of waste management hierarchy, we're always looking at ways to prevent the flow back being generated in the first place. Eric touched on a few prevention methods using alternatives. Propane's one of them. Difference being between propane and water, you can't really pipe propane into the site. So again, that increases truck traffic, so we need to balance up the pros and cons. In terms of optimisation, reduction, what that means is basically do your desktop research, understand the geology, carry out the 3D surveys, look where you're going to focus your hydraulic fractures, and understand how big those fractures could potentially be, and then that will probably give you a good indication of how much water you need to inject. Reuse, we're currently looking at this in quite a lot of depth, and we are talking with the Environment Agency. Tends to be that we are going down the route of reusing flowback fluids during hydraulic fracturing stages. So this basically eliminates all flowback going off-site, which is a big win for the industry. Recycling, again, as Eric touched on this, we are seriously looking at this with a number of contractors. I'll touch on a case study as well over in the States, which looks at recycling flowback fluid. It's a bit of a no-brainer for us. If we can take trucks off the roads, if we can then produce a distilled water on site, we can then reuse that for further hydraulic fracturing, and also provided us with other options as well of how to treat flowback fluid, probably more commercially savvy as well. And finally, disposal off-site. We do have a number of options available to us. There are a number of sites, probably a handful with existing RSR permits and waste management permits to deal with raw flowback fluid and can be managed and disposed of in accordance with UK regulation. So in terms of the behaviour of flowback, there's probably a bit of a misconception again in the communities that there's this constant return of fluid that comes out of the well, which simply isn't the case. As you can see, in the first probably 7 or 8 days, you get a concentrated flow coming back after the initial injection. So you're looking at 3 barrels a minute, so that's what, roughly about half a cubic metre per minute. This is an example from a play over in the US, but again, that depends on how much you inject in the first place, but also depends on the geology, how much it kicks back out or absorbed into the geology itself. Again, we can control that flow by simply saying if we get a lot of flow back, Eric and his team can control those flow rates, and we can store flow back on site. So it's not a process which is something that just freely flows back. It is a controlled process. Then over a period of days, it settles down into very small quantities that flow back. Then hopefully there'll be a transition period. This is where the gas kicks in, and that's when obviously we start supplying that into the mains. Elswick, we probably empty the flowback tank probably 4 times a year. So that's been going since the mid-90s. So very small quantities of flowback fluid created. So when it does come to the surface, we use something called green completions. So it flows up out of the well. It's under pressure. If we just identify, it's a little bit of engineering here called a choke manifold that reduces the pressure. It then flows into a separator. It's a 4-stage separator, so that will separate out the water, the sand, any condensate and the natural gas. The natural gas will then flow off into this direction to either be flared or go into the national grid. You'll probably have a sand bin on site to get any of the return sand, and a condensate bin as well. And then the flowback simply goes into these tanks here. We don't use any open lagoons, which has been practiced over in the US. We use steel flowback tanks. And this is located on an impermeable membrane as well, so that provides the secondary containment. Now you can also get flowback tanks which are double skinned as well, so then you're getting into tertiary containment as well. And that's what it looks like. I know Eric explained the difference between drilling and hydraulic fracturing. Probably what someone might say is, hang on, you've got a lagoon here. What this is just a rainwater ditch, because obviously you stick an impermeable membrane on a site, it's going to collect a lot of rainwater, especially in the northwest. And again, this could provide a source, as long as it's clean, tested, analysed, and it's good to go. that can be used during drilling and also during hydraulic fracturing as well. So as I mentioned, we've got a number of off-site disposal facilities. They again have to meet EPR regulations under the Waste Management and RSR. And again, we have to make that link during the EIA process and also during the RSR process to say that, yes, we're going to produce it, we're going to manage it on site in accordance with the permitting, and by the way, we've also got the off-site facilities which are permitted. On-site treatment, so as I mentioned, we are looking into this. There's a number of technologies that exist, flocculation, evaporation, ion exchanges. It's readily used over in the US now, so you know, it's something which Quadrilla ourselves, and I know we're pursuing it, it should be basically normal practice. However, we still need to go through the process of getting regulatory and social acceptance, say that we're going to start treating waste flow back on site. We still haven't broached that one with communities yet, so we need to go through that process of education and making them understand and listening to concerns and taking them on board. So in terms of a case study in the US, sorry, apologies about my geography, I've said case study in the US and it's a case study from Canada. Thanks. So there's a company called Apache. They're pretty much leading the way in terms of environmental management and their credentials within this field. They're operating in the Consort field, which is quite a remote location in Canada. They've got no access to a large supply of water or mains water, but within the local vicinity there was a village, and they realised that they were producing waste effluents, about 19,000 barrels per day. So someone within Apache had a great idea, saying, well, you know, let's utilise that as a hydraulic fracturing fluid. So they employed a mechanical and chemical treatment works, cost them about $400,000. They then cleaned up the waste effluent, re-injected that and injected that into the formation, and they reckon on the whole it saved them about $1.4 million overall. And it's meeting the commitment to reducing the amount of fresh water that the industry utilises. So it can be done. Obviously, we don't have the remoteness of Canada, but however, you know, case studies like this really does appeal to me as an environmentalist, but also to us, probably from a commercial point of view. If you see that figure of 1.4 million in terms of cost saving, again, probably one of the biggest barriers to that is not necessarily the engineering, but more the social acceptance and trying to work through the regulatory regime as well. But again, through the education process, the community engagement, this could be the norm. So in terms of conclusions, I was having a look at the CIWEM recommendations, so kind of try and touch on some of the points. Is that yes, we are actively engaged with Arup to provide an EIA assessment, not from a position of advocacy, but from a position of objectivity, based on science, based on models. And what that's telling us will influence how we go about our operations, and that also accounts in the cumulative impact of our activities. The USA is a quite good case study. Obviously, they're probably about a decade ahead of us. Data shown from the US, despite the shale gas boom, investment in renewables is continuing to rise. Probably Mark's better the place to talk about this, but engagement with local community business regulator, this forms part of the planning process and the environmental impact process, as well as the ERA, but also we make quite active steps to get involved with the community and again promote our message and understanding of hydraulic fracturing. Environment Agency produced, I know we touched on it, GP3 guidance, so this provides us with real good understanding of where we can and cannot operate in terms of drilling and hydraulic fracturing, in terms of protecting groundwater, and also the mitigation measures which we need to employ, so putting in multiple barriers, cementing, casing, integrity testing, good well integrity, which is controlled by the HSE regulators. One of our key stakeholders is the utility providers, so we actively work with United Utilities in the Northwest. I know probably from the CIWA recommendation is that they become a statutory consultee. Regardless, from our perspective, it's a no-brainer. Again, we need to work with these guys both from the supply of water, but also they've got a whole network of wastewater treatment plants, and they're experts in that field. So it provides us with really good expertise to engineering knowledge for the treatment of flowback fluid. Also, as Eric was talking about, we do install a microseismic array to monitor hydraulic fractures, understand the growth, understanding where the faults are, etc. So, sorry, that's from the 3D seismic, but monitoring the hydraulic fracturing gives us that ability and confidence to let the community know where the hydraulic fractures have gone. We do commencement of baseline data before operations. Again, that's probably protecting ourselves, but also that's a good demonstration that when we go back to P&A in the well, we've restored it to its original conditions. There's a lot of guidance out there. We operate to UKOG guidance as well as Environment Agency pollution prevention guidelines, and that will be demonstrated through our management plans, which will be submitted in the Environment Impact Assessment. And as I've mentioned numerous times, we are actively looking at recycling water and reusing water. And again, technology is readily available, so it should be happening here very soon. What I just wanted to conclude on is probably a comparison. At the moment, there's a site going through an EIA process and permitting. As you can see, the site is located here. This is a geothermal well. It's in the centre of Manchester. They're going to be drilling down to about 3,000 feet, 2 wells. They'll then do some laterals about 500 metres. They're installing a microseismic array, and they'll be stimulating the well, obviously, to get the geothermal fluids coming to the surface. Sounds pretty similar to hydraulic fracturing. But socially acceptable. It's right in the city centre, in communities, and it's going ahead and has the same hallmarks of what we're doing. So again, there's a few pros and cons as well in trying to get that message across to communities, but clearly education is the way forward for us to promote the message, because these guys are doing it in the centre of Manchester, and I think if we turned up in the centre of Manchester and said we're going to hydraulic fracture there, I think there might be a few concerns. Okay, so that's the presentation. I know I've probably just touched on a small area of environmental impacts, etc., but I guess we can explore more though in the Q&A session. Okay, thank you.